Good afternoon, friends. Today I would like to discuss parametric test. There are four parametric tests, namely chi-square, T, F and Z. So out of these four tests we discuss the first one, that is chi-square test. So basically when we have qualitative data, when the variable is qualitative, then the chi-square test is used. So it is basically used for testing the goodness of fit and test of independence. So in case of a goodness of fit test, for example, we are interested in testing, that means whether the sample results conform to the specified expected probabilities or not. So that can be tested by chi-square test of goodness of fit. So for this we take one example, that is we have a data about technical support calls for various days of the week. So here the question is, are the technical support calls equal across all days of the week? That means whether the calls follows a uniform distribution or not. So this hypothesis we want to test. And the data is, we have for 7 days of a week, the number of calls arrived are listed on the slide, and there are total 1722 calls overall. Now we want to test the hypothesis, the distribution of calls is uniform over days of the week against the distribution of calls is not uniform. So here the first one, H0, that is called the null hypothesis, and H1 is called the alternative hypothesis. So to test this hypothesis, actually here our objective is to test whether the observed frequencies, so these are the observed frequencies, observed data and expected data. Expected means we expect that it follows a uniform distribution. That means all these 1722 calls are uniformly distributed over the 7 days of the week. So the hypothesis is the distribution of calls is uniform over days of the week against it is not uniform. So to test this hypothesis we have to calculate expected frequencies. Expected means assuming that the null hypothesis is true. That means the calls are uniformly distributed. So that means if the calls are uniformly distributed, then the total number of calls for all 7 days, that is 1722 calls, would be expected to be equally divided across the 7 days. That means on an average per day the expected number of calls equal to 246, that is total number of calls divided by 7 days of a week. So expected frequency or expected number of calls per day is 246 if we assume uniform distribution. So this chi-square test of goodness of fit is used to test to see if the sample results are consistent with the expected. That means we have the observed data and we calculate the expected frequencies as per the uniform distribution, and then we compare the difference. That means is there any significant difference between the observed frequencies and expected frequencies. So that can be tested by this. So here again we have same, the first column is the days of the week, second column is observed frequencies, whatever the data we have collected about the number of calls, that is the second column, and the third column is expected frequency. So under the null hypothesis all the calls 1722 calls are uniformly distributed, so the expected frequency is same for all 7 days, that is 246. And for testing the hypothesis, the chi-square test statistic, the chi-square test statistic is chi-square equal to summation from 1 to k oi minus ei whole square upon ei. Here k is the degrees of freedom, k is the number of categories, oi that is observed frequency for ith category, ei observed frequency for ith category, and for this chi-square test statistic the degrees of freedom is k minus 1. So by using this observed and expected data OI and EI, one can calculate this test statistic. And here the rejection region, if you observe the graph of chi-square distribution, it has a longer tail towards right side, and there is a shaded portion, red portion, that is the probability rejection region, that is the rejection region. And if you observe that number, that is chi-square alpha. So below chi-square alpha, if the value of chi-square falls below chi-square alpha, then we reject the hypothesis, otherwise we accept the hypothesis. So we have the entire chi-square region is classified into two categories. One is called the rejection region, that is the red part, and the other is called, that is acceptance region, that means where we accept the hypothesis. So by using the test statistic, here this is the test statistics, summation OI minus EI square upon EI, and I is from 1 to k. So using this test statistic, one can calculate the value of statistic, that is chi-square, and that is 23.05. Here k is the number of categories, so there are 7 days of the week, and the degrees of freedom is k minus 1. So the table value of chi-square for 6 degrees of freedom and at 5% level of significance, that is tabulated value, that is 12.59. And from the graph one can see that if the value of chi-square calculated, that means calculated from the data, that is 23.05, it falls below that chi-square table value, then it is the hypothesis is rejected. So in this case, chi-square calculated is 23.05, which is greater than the observed value chi-square 12. So reject the hypothesis. So the conclusion is the distribution is not uniform. That means if you observe this data, that means the calls are not uniformly distributed over the days of the week. So this is one application of chi-square, that is test of goodness of fit. But many times we have the distribution involves some parameters. So chi-square test for goodness of fit is also used for testing the various distributions, that is binomial, Poisson or normal. Now let us take one example. Now in this case also it is the test statistic is same, summation OI minus EI square upon EI, but except that the number of degrees of freedom for the chi-square random variable is not k minus 1, but it is k minus m minus 1, where k is the number of categories and m is the number of parameters to be estimated for the distribution. So let us take another example. Here we have bank customer arrival data. So number of customers arrived, so that data is given here, and we want to test the hypothesis. That means this is the actual data, observed data. So this frequency distribution follows Poisson distribution or not. So this we want to test. So here number of arrivals 0, 1, 2, 3, 4 and more than 5. So these are the observed frequencies. Now again here we calculate the mean, because we want to test the hypothesis about the Poisson distribution, and Poisson distribution involves one parameter, that is lambda. So lambda can be estimated by sample mean. Now we have the observed data. If you observe this is the observed data. So from this observed data, these are the values of x, these are the values of frequencies, and from this one can calculate f into x. Their total is 192. So the sample mean is summation fi xi upon summation fi. So it is 192 upon 84. So it is 2.3. So this is the value. This is not the value of lambda, but it is the estimated value of lambda. That means average number of customers per minute. Average number of customers arrived per minute. So it is also called mean arrival rate. So in this way one can estimate the parameter involved in the distribution. Then by using the Poisson probability law, one can calculate the Poisson probabilities. So these are the Poisson probabilities for various values of x. So for x equal to 0, the Poisson probability is 0.1003 and so on. These are Poisson probabilities for lambda equal to 2.3. And here n, that is total number of observations. So we have 84 observations, sum of the frequencies. So total number of observations. Now once we have the Poisson probabilities, so if you multiply that Poisson probabilities by n, the number of total number of observations, we get the expected frequencies. So these are the expected frequencies. So if you observe this is the value of x equal to 0, this is the observed frequency. But if the data follows Poisson distribution, that means under the assumption that it follows Poisson distribution, the expected frequency is 8.42, and the test statistic is again same, only slight notational change is there, that is FO minus FE upon square upon FE. So in this way one can calculate. So this is the FO means observed frequencies, FE means frequency but expected. So this is that column. So using this particular formula we get chi-square test statistic as 1.74. It is 1.74. Now here again alpha is 5% level of significance, then degrees of freedom is k minus m minus 1. So here there is a mistake, k minus m minus 1. So m is the number of parameters estimated. So in this case we have one parameter, that is lambda, we have estimated lambda. So it is k minus 1 minus 1, 6 minus 1 minus 1. So degrees of freedom is 4, and now the tabulated value of chi-square, that is chi-square with 4 degrees of freedom and 5% level of significance, that is 9.488. So here again we have the same type of graph, chi-square graph. So here this red portion is the rejection region, and this portion is gray portion is the acceptance region. So the value of calculated value is 1.74 and tabulated value is 9.488. So calculated is a less than table. It means that we do not reject the null hypothesis, right? That means we accept the null hypothesis. So that is frequency distribution is not Poisson distribution. So now contingency table. So the another application of chi-square is contingency table. That means test of independence. So in contingency table what we have? So contingency table is used to classify sample observations according to a pair of attributes. Attribute means qualitative character. So this is also called a cross classification or cross tabulation table. So suppose we have two attributes and the two attributes A and B are categorized into respectively R categories and C categories. So A attribute is classified into R categories, B attribute is classified into C categories. So in this way we have this type of table, that is R by C table. So this table is known as R by C contingency table. So here A attribute is classified into R categories, B attribute is classified into C categories, and we have these values at the intersection of each cell. This is O11, that is observed frequency for first category of attribute A and for the first category of attribute B. Similarly we have other values, and the last column, that is row total, that is the row total, and this last row, that is a column total, and here this is the total of all observations, that means total of row total and total of column totals. So suppose we have n observations tabulated in R by C contingency table. Now this Oij, in general this Oij is the number of observations in the cell, that is in the ith row and jth column. So in this case our hypothesis is slightly different because we want to test association or independence. So the null hypothesis is no association exists between the two attributes in the population. So again for this type of hypothesis testing problem, the test statistic is chi-square with R minus 1 into C minus 1 degrees of freedom. So here let Ri and Cj be the row and column totals. Then the expected number of observations in cell row I and column J given that H naught is true. So what is H naught here? H naught is no association. That means they are independent. The categories are independent. So if they are independent, then by the law, probability law, we have Eij equal to Ri into Cj upon n. Eij is the expected frequency for ith row and jth column. Ri is the row total for ith row. Cj is the column total for jth column, and n is the total number of observations. So again, if you look at the test statistic, it is similar to the previous one. Only the difference is, since here we have two-way table, so there are double summation. So it is chi-square statistic is double summation Oij minus Eij square upon Eij, and the rejection, that means the decision is reject H naught if chi-square calculated is greater than the chi-square table value. So here let us consider the example, numerical example for this contingency table. So let us discuss first of all 2 by 2 example, 2 by 2 contingency table. Suppose we have a data about students, their gender, and about dominant hand. So some are left-handed, some are right-handed, some are male, some are female. So in this case, our null hypothesis is there is no association between hand preference and gender. That means hand preference and gender are independent of each other. Against the alternative hypothesis, hand preference is not independent of gender. So, and this is the observed data. So we have taken a sample of size 300. So out of 300 students, 120 are female, 180 are male, and again out of 300, 36 are left-handed, 264 are right-handed. And here this is cross classification. That means out of 180 female student, only 12 are left-handed and 108 are right-handed. So in this way we have the 2 by 2 contingency table, and the sample size is 300. So in this case of hypothesis, there is no association between hand preference and gender. Against, there is a association. So obviously if the null hypothesis is true, that means there is no association. If there is no association, then the proportion of left-handed female should be same as the proportion of left-handed male. That means the proportion is same. So the two proportion above should be same as the proportion of left-handed people over all. So to calculate the expected frequencies, so we have 120 females and 12 were left-handed, 180 males and 24 were left-handed. So overall probability of left-handed equal to 36 divided by 300, because out of 300, 36 are left-handed. So the probability is 0.12. So if there is no association, so probability of left-handed female is same as